So welcome everyone to the closing session of the traditional IFT Xmas Workshop. And it's really a great pleasure to have for this closing talk, Zoltan Fodor from Penn State University. So Zoltan has given very important contributions to the study of QCD thermodynamics and QCD at zero temperature through Lattice Qcd simulations. And this year, together with the Budapest Marseille Wuppertal collaboration, Lattice collaboration, he has published the first sub-percent precision results for the most important contribution, the Hedronic contribution to the muon g-2. And we have just learned that today the Science magazine has announced this among the breakthroughs of the year. So we're extremely excited to hear about this. Thanks very much, Zoltan, for joining. Please, whenever you want.
Thank you very much. Thank you very much for the kind invitation and this nice introduction, and for the opportunity to speak about the g-2 of the muon from Lattice Qcd and experiments. And as I will tell you, and that made some excitement, there are signals that we might have found new physics, or perhaps not. And that's the topic I'm going to discuss. This is very early time here because I'm in the US, so it's probably not the best talk I've ever given. So I have to apologize if I'm a little bit still sleepy. So as you have heard, this work is done in collaboration within the Budapest Marseille Wuppertal collaboration. Some people call us BMW. So if you see these three letters, then this is the collaboration, what we have, about 10, 12 people. So there was an announcement on April 7th this year at the Fermilab, who measured the magnetic moment of the muon, and on the same day our Nature paper has been published, and the general press just jumped on the topic. So from the Frankfurter Allgemeine Zeitung to Forbes magazine, from Wall Street Journal to Le Monde, from the New York Times to Yahoo News, many newspapers reported about these results. And for instance, the New York Times had the story on its opening page for 2 weeks, which is very seldom in science. And I just learned today, because that was announced today, that this topic, the experiment and our calculation, was announced to be one of the breakthroughs of the year 2021, with the sentences that on the same day experimenters released their result, one team of theorists, that's our team, published a calculation that they argued increases the standard model prediction and closes the observed gap. So how does it look like? And this is the most important message I want you to bring home, this small figure. So on the horizontal axis, I have the magnetic moment of the muon, actually just the 8th and 9th digits, because the measurements and the theoretical calculations are so precise that that's the place where we see the differences. The experimental average is shown by this purple band, and it is published in this paper in PhysRev letters. And this is in 4.2 sigma disagreement with the so-called white paper result. This is 134 physicists analyzing all the details of the magnetic moment. Here is the publication detail, and it goes under the name of white paper, or R ratio method, or theory consensus result or other names. And somewhere between them, there is our result. The publication is given here, the BMW result, which has a 1.5 sigma tension with the experimental average, which is nothing really serious. And even the tension with the white paper or R ratio method is 2.1 sigma. And as I used to say, if you find a 2.1 sigma effect, you might be able to be invited for a seminar, but most probably you have to pay for your travel costs. So this is the situation, and let me emphasize that Lattice QCD, and I was told that the audience is rather mixed, so they have probably less direct contact with Lattice QCD results. Lattice QCD is already something which delivers precise and scientifically solid results. And I just listed here 4 of the results of our group. Here is the nature of the QCD transition in the early universe, which turned out to be an analytic crossover. This is the hadronic mass spectrum. Here you see all the particles, you know, pi on k on rho k, nucleon lambda sigma psi, and so on and so forth. A few years later, we were able to even determine the mass splittings within these multiplets. For instance, this is the mass splitting in the nuclear sector between proton and neutron. And another result is here, the equation of state of the early universe given for 5 orders of magnitude. So far, so good. Let me show you my outline. First, I will say a very few words about the g-2, mostly to fix my notation. And then I will go along this plot, first discussing the purple band, then the green band with the R ratio result or white paper result, and then spend most of the time on the lattice results. So the muon is the first particle which was discovered, except for ordinary matter in the atmosphere. It has the same electric charge, the same spin than the electron. However, it's 207 times heavier, which means that it has a finite lifetime, which is 2.2 microseconds, and that plays an important role in the experiments. The question is how strong its magnetic moment. And the experimental technique, what we will see is goes back to the idea that if you have a magnetic moment in a magnetic field, then it will precess. And if you have a circular current, then the magnetic moment is given by this formula. If you have a spin particle, then it is described by the Dirac equation. There is a factor of 2 here, which we call G because it's not exactly 2. It's about 1 per mil larger. And the anomalous part, which is g-2/2, is A, and that's the number I will be focusing on in the rest of my talk. So let me come to the experimental result. The newly announced, newly means April, announced Fermilab result is given here for A mu, which I just defined on the previous slide, which is a 0.46 precision per million. This is equivalent to a bathroom scale, which is sensitive to the weight of a single eyelash. This result fully agrees with the 20-year-old Brookhaven experimental result, which is written here. So the combined result has an even smaller error, and a lot of experimental results are on tape at Fermilab, and they anticipate the target uncertainty in this last digit to be reduced from 4.1 to 1.6. The experiment goes back to many, many decades. The experiments are older than I am. And here are these findings where you see the errors in brackets. And as you see, it dropped dramatically all the way down to the present accuracy. So it's not surprising that the most precise experimental results came from Brookhaven, because they had a very good magnet, which is a $30 million magnet, but they didn't have enough muons. And Fermilab had the most intense muon beam in the whole world. So the idea was to bring these two things together. So they decided to bring these 14-meter diameter magnet ring to Fermilab laboratory. And 14 meters means 3.5 lanes in a highway. So it cannot be done on the roads, because then you have to probably build new bridges or tunnels or whatever. So what they did, they put it on a boat, they sailed down in the east coast of the US, then went around Florida, and on the Mississippi, they sailed up to Fermilab, where the last few miles were done on roads. And here is the celebrating physicists who are happy that the magnet arrived without any problem. Without any problem means that even 1 millimeter bending would have been a disaster for this magnet. So the magnet is at Fermilab. It has a magnetic field of 1.45 Tesla, and there is a special momentum 3.094 GeV, which is used, and it makes the experiment more controllable. So what is happening here? We are shooting the muons into the storage ring, and there is a cyclotron motion with this frequency. So the muon, because it's a charged particle, is going around. At the same time, there is a precession frequency, which is almost the same as you see, and the difference is proportional to this A mu, which we just defined 3 slides before. So what is happening that when the muon is going around and the blue arrow shows its momentum, then the precession is going a little bit faster. So the green arrows, which are showing the spin direction, are turning a little bit faster. And that gives then A mu directly. And the exact number is that after one round around, the spin axis changes a little bit. This is a little bit exaggerated. The real number is 12 minutes. So the pions are produced at a fixed target, pi plus, and this pi plus is then decaying into mu plus and neutrino. And as we discussed, the muons are decaying, and there is a strong correlation between the muon spin and the positron momentum. That means that we can detect actually the direction of the spin. And that direction is oscillating, because after a while it goes back again to the direction of the momentum. And this oscillation can be then seen in the experiment, and measuring this oscillation frequency, you can directly obtain a mu of the muon. So that was my very short summary of the experimental part. And let me move on now to this white paper prediction of the muon magnetic moment. So the muons has a lot of virtual particles around it, and the contribution to the anomalous magnetic moment is coming from quantum electrodynamics, from the electroweak theory, and from the strong theory. There's nothing really surprising here, but let us look at the numbers. So the white paper, they listed all these three contributions. The QED contribution is far the largest with 0 error in it. The electroweak is much, much smaller with also a negligible error. And the strong contribution is between the two, and the error is fully dominated, 100% dominated by the strong contribution. So we should remember this 15 because it's an important number, and the 693 for the rest of the talk. And I will usually use these units, so I multiply everything by 10 to the 10 to have a number which is easier to work with. So again, 15 and 693. So what can we say about QED? The fine structure constant is much smaller than 1. So it is a rapidly converging series. Here is the 1 loop result, 2 loop, 3 loop, 4 loop, 5 loop result. And here is the total result, what you have. Here are the graphs. This is the 0th order graph. This is the 1 loop graph calculated by Julian Schwinger, who got the Nobel Prize for that. And here are the higher order terms. And the 5 loop result was calculated in a heroic work by Kinoshita et al. It had over 10,000 diagrams. Obviously, you're not drawing them by hand, but there is an automated diagram generation. Actually, it is still not confirmed by other groups, but it doesn't matter because the error associated with leaving out this term is negligible. So we are absolutely certain that the electromagnetic part is as it is. Then we have the Hedronic contributions, which is the second largest, and there are several types of them. So this is the so-called leading order Hedronic vacuum polarization. The muon is coming in, emitting a photon. There is a Hedronic loop here, which goes into a photon, and that's absorbed by the outgoing muon. This is the leading order vacuum polarization. You can have next to leading orders with adding different graphs to that. I will come to this point later. And there is a so-called Hedronic light by light contribution, light by light, because this hadronic bubble has 4 photon lines. So it's somehow a photon is scattering on another photon. This graph was considered to be the hard part, but in the meantime, it seems to be that the precision what we need is already reached, and we have very good agreement with phenomenological and lattice determinations of this Hedronic light by light contribution. So the Hedronic vacuum polarization is obviously not converging. In QED, we had these 1/137, which was a small number and converged. But in QCD, we are at low energies. The strong coupling constant is about 1, and all perturbative approaches fail. The solution to that, and that goes back also many, many decades, is the Hedronic vacuum polarization from the R ratio. The R ratio is the ratio of the hadronic cross-section over the muonic cross-section of electron-positron collisions. Here is the R ratio as a function of the center of mass energy. And you see here several peaks and a very delicate structure. We had a lot of E plus, E minus going to hadron data from these experiments. And once you have it, then you can use the optical theorem, which tells us that the graph, what we are looking for, that was the graph, is linked to the R ratio. So gamma goes to all hadron squared. And you have some kernel function, integrate, and then you have the leading order hadronic vacuum polarization. Here are a couple of works which have calculated that. And here you see these numbers which are scattered around 692.93, the number which we already discussed. Coming back to the next leading order, next to leading order contributions, they are small and their error is much smaller than the errors of the leading contribution. So it seems that we should deal with the leading order vacuum polarization. And let me tell you that when we are hunting for new physics, why it is the case. So here I show you the result compared to the experimental result in these 10 to the minus 10 units. So if I consider the experimental results with its error, then the white paper result or these DHMZ or KNT or all these theoretical results obtained from E plus, E minus and the dispersion relation, they are all below the experimental result. Actually, the difference is something like 25. And you remember the electroweak contribution was 15, so it's almost twice as large as the electroweak contribution. And that's these 4.2 sigma significance between the R ratio method and the experimental method. So if you hope for new physics, then the good news is that Fermilab has a plan, and they will reach the experiment instead of this experimental error, a 1.6 experimental error, and that would increase the discrepancy from 4.2 sigma to 6 sigma, even if the theory is not improving. If the theory is improving, let's say the light by light goes down to 10%, the error, and the HVP error goes down to 0.2%, then the discrepancy will be 11 sigma, and there is no way you can argue that there is nothing there. There must be something, some new physics. If you believe for no new physics, then you can look at what do you need for that. You might think to increase the vacuum polarization part by 4%. And then it would be, instead of 693, it would be something like 720. Or you might hope that the light by light contribution will be 360% larger, but the error is so small on it that it is very unlikely that the light by light contribution could be so much larger. So that's about the white paper or R ratio or dispersion relation or theory consensus determination of the Hedronic contribution. Let me move on and discuss the Lattice Qcd results. So as you all know, we integrate over all classical field configuration. That's how Lattice Qcd is working. So here is the action with the gluonic part and the fermionic part, and then we integrate over all gluonic fields and fermionic fields. And today, typical lattices in this business are around 100 lattice points, which means several billion dimensional integrals. This is obviously done in a stochastic way. One of the most important resources which we have used is the Juwels computer in Forschungszentrum Jülich in Germany. And that was about 100,000 years for a laptop, the calculational need, which is 1 year for such a supercomputer, what you see here. The lattice gauge theory is a systematically improvable and non-perturbative method, which is using just the Lagrangian. That's why we call it first principle. We discretize space-time, put quarks on the sides, and the gluon fields, the gauge fields, we put on the links between these sides. And instead of integrating, we are summing over all the points, and the derivatives are taken as finite differences. And in order to get physical results, we need two very important steps, and I will speak about them in detail. First, we need the infinite volume limit, because the world is not a box, a small box. And we need a continuum limit, meaning this lattice spacing is going to 0. That's how we will recover the continuum result. We will have several lattice spacings, and we claim that you need at least 3 different lattice spacings to be able to extrapolate to 0 lattice spacings, but I will discuss this issue in more detail. So what we do is we are calculating here the electromagnetic current correlator. We call it CT. And then we multiply it with some kernel function, which describes the leptonic part of this diagram. And that gives us the leading order Hedronic vacuum polarization contribution to the muon's magnetic moment. In this plot, I show you this current correlator multiplied with this by this kernel function as a function of t, as a function of the Euclidean time. And what you see here is a somewhat peaked structure, peaked around 1 Fermi. And for larger distances, you see more and more noise. The blue results are 2020 results, and the red results are the 2017 results. And as you see, we were able to reduce the noise a lot. So the simulation setup consists of 6 lattice spacing. So I said at least 3, we had 6. So we think that we can control the continuum extrapolation very accurately. We usually have a box size of 6 Fermi, but since we have to deal with finite volume effects, we will also have 11 Fermi boxes. Just remember, 1 Fermi, or 10 to the minus 15 meter, is about the size of a proton. So this plot shows the various lattice spacings shown by various different colors. And this is a proxy for the light quark, and this is a proxy for the strange quark. As you see, they are all scattered around the physical point, which is the black point. So we don't need any chiral extrapolation anymore. Instead of, we will have a chiral interpolation to this black point. These are the gauge couplings which determine the lattice spacing. And the lattice spacing determines the size of the lattice, since we want to have 6 Fermi. And here I list the number of configurations. In order to have the same precision at fine lattices as we have at coarse lattices, we had to increase the number of configurations, number of independent gauge configurations by about an order of magnitude. If we wanted to reach these sub% accuracy, which we heard in the introduction, then we had 4 challenges. We cannot neglect the QED or the isospin breaking effects anymore. We have to have a very precise lattice spacing. We have to reduce the noise, and we have to get rid of the finite volume effects. And I will do all 4 and shortly summarize all 4. Of course, I cannot discuss all the details because the paper is well over 100 pages. So if you are interested in the details, then you can look it up there. So let me start with the lattice spacing or the scale determination. So the lattice spacing A enters at 2 places. It determines the physical value of the muon mass and the physical values of the hadron masses, such as the pion and the kaon masses. And a back of an envelope calculation shows that if you have an error on A mu, let's say 1 per mil, then it is actually doubled the error of the scale. So if you want to have 1 per mil, then you have to have half per mil error on the scale. And of course, you have many more sources of uncertainties. So it's definitely not enough to have here such an accuracy. So for our final result, we use the omega baryon mass for scale setting. The lattice spacing is the measured omega mass in lattice units divided by the experimental omega mass. It is experimentally very well known. It has very moderate quark mass dependence and it can be precisely determined on the lattice. In addition, an intermediate step was also used, the so-called W0 scale setting, which also has moderate MQ dependence. It can be also precisely determined on the lattice. Unfortunately, it has no experimental value, so we determine it from m omega times W0, and then using the value, the physical value of m omega, we can get the W0 value, which is given here. The other topic was the noise reduction. So as we always experience, the noise over signal grows for large distances. And that's what you see for this current correlator, that the red points have larger and larger errors as we are increasing the distances. The technique to get rid of that is the so-called low mode averaging. We use the exact all-to-all quark propagator in the infrared region. That means large distances, and use the stochastic technique in the UV region. In addition, there are strict upper-lower bounds on this correlator, and we also use that. All in all, we were able to reach a few per mil level accuracy on each ensemble. The next topic is the finite size effect. So typical lattice runs were done on 6 Fermi lattices, but earlier model estimates gave about 2% finite volume effect between 6 Fermi lattice and the infinitely larger lattice. So what we did, we have chosen a reference lattice size, about 6 Fermi, and the so-called big lattice, which was about 11 Fermi. And then we determined, using lattice simulations, the difference for A mu between the reference lattice and the big lattice. And here is the result. That's the difference. It is dominated actually by statistical errors. And then we had a couple of, or several theoretical models. Next to leading order chiral perturbation theory, next to leading order chiral perturbation theory, so-called MLLGS model, Hanson-Patella model, and the Rho model. And what we see that except for the next to leading order chiral perturbation theory, all the others are in fairly good agreement with the lattice measurement. That's good news, though we don't want to use for the difference between reference and big these models. We want to use our measurement, but for the difference between the big lattice and an infinitely big lattice, we can use these models because they are getting better and better as we increase the volume. At the end of the day, we use these models for the remnant finite size effect, and the error is turned out to be now about 0.1%. And finally, there are these isospin breaking effects, and here I give you all the results of the various graphs, for instance, QED isospin breaking valence sector, the strong isospin breaking, a QED isospin breaking C sector, and a QED isospin breaking mixed sector. And here you see all the numerical values. So all everybody in the community have the chance to check them and point out if there were any error in these calculations. The final result is 707.5. And you remember that the R ratio method gave 693. So that's why the sum is larger, because this contribution was larger. And if the sum is larger, then we are closer to the experimental value. And here it is. So the no new physics scenario would require something like 720 for the hadron vacuum polarization. Our result is actually touching it. The other lattice results have much larger errors, so they cannot really discriminate between the no new physics scenario and the 4.2 sigma tension claimed by the R ratio method. So all in all, our result has a 0.8% accuracy. It is consistent with the Fermilab experiment, but 2 sigma larger than the DHMZ, Davier and collaborators, and 2.5 sigma larger than a somewhat more aggressive KNT result. It was a very surprising result for us because in some sense we are comparing QCD with QCD, and you don't expect differences on that level. So there is one way to cross-check very easily our findings, and that is the so-called window observable. It was introduced by the RBC UK QCD collaboration, and it is cutting out the contribution between 0.4 Fermi to 1.0 Fermi. which is good because you don't have to deal with the large tail here, which is very noisy, with your window function, which multiplies your original correlator. This term, this part is vanishing. And you don't have to deal with this part, which is the small distance contribution. And at small distances, you also have cutoff effects. So here you have noise, here you have cutoff effects. In between, you have essentially nothing.
Sorry, can I ask a question about this plot?
Absolutely.
So the red points at exactly 4 Fermis, they seem to have a transition. I mean, there is an offset. So is it just due to noise, or is there something happening at 4 Fermis?
This is just noise.
It's just noise, okay.
Noise. Yeah.
So there's no possible systematic happening on the code or whatever.
No, essentially not. And as I said, this is the red points are already superseded here, as you see. There is nothing around 4 Fermi if you take the most recent data.
Yeah, okay.
In the old data, there was perhaps some strange behavior, but in the new data, in the new and more precise data, which would have been possible to see any such jump, there is no jump whatsoever.
Yeah, okay. Yeah, thank you.
Sure. So coming back to the window, again, we multiply the original function by this window function, and that's what you obtain, and you can integrate this thing too. So here the signal per noise is eliminated. Finite size effects are also smaller because the finite size effects are usually dominating the large distance behavior. And the lattice artifacts are also small because these cutoff effects are also cut off. So this is something very easy to measure. To measure this quantity is about 1 or 2% of the total computational costs and 1 or 2% of the total manpower cost. And what we have is shown here. So this is the lattice spacing squared going to 0 with various techniques, leaving out the coarsest lattice, the coarsest and the second coarsest, using linear or quadratic or even higher order extrapolations all the way down to the 0 lattice spacing. And if you do that, then you have something like that. This is the central value, 207 something, with an error which is shown here, which includes 68% of all these fits. And surprisingly enough, this is much larger than the R ratio result, which needs a little bit of adjustment used by lattice results, but the discrepancy is something like 3.7 sigma. So here the difference, the tension is even larger than for the total mu. And the reason for that we can measure this quantity much more precisely. Many groups have done that.
So
Yes?
may I ask, so the plot below corresponds to the use of the window observable in both cases, or did I understand that correctly or not?
So
or
this is the
for
window
full...
observable. This
okay.
is
Yeah,
as a function of the lattice spacing.
Okay, thanks. Yeah.
And extrapolate it to 0 lattice spacing.
Okay.
With this result. And there is a tension between the lattice and the R ratio technique, which is about 3.7 sigma.
Yeah, thanks.
Did I answer your question?
Yes, thank you.
Sure. And other groups also measured that quantity, this ratio or this window quantity, because it's, as I said, it's 2 orders of magnitude cheaper and less manpower intensive. And this is the value of the R ratio. And interestingly, all the other findings are above. Well, some of them a bit larger or some of them a bit smaller error, but interestingly, all of them are above this R ratio value. Since the tension between theory and theory is the largest at for this window observable, we carried out an additional analysis, which is a very expensive analysis, and we have done it with overlap fermions. So people might say that staggered fermions are essentially wrong or not necessarily controlled, but overlap fermions are the theoretically cleanest fermions. And if they give the same result, then there shouldn't be any problem. And here is the result, again, for the window observable. Now for 3 Fermi boxes and not 6 Fermi, because overlap is very expensive. And again, the window observable is a function of the lattice spacing squared. And this is the overlap on stout result. And this is the stout on stout result. And as you see, they agree completely. So the difference between them and the error between them is about 1 unit, 96, 97. And here the difference was 7 units. So despite the fact that the overlap is not as precise yet as it could be, it's very hard to imagine that this discrepancy disappears soon. And a few final remarks on the continuum limit. So here I show you the AMU light quark contribution, which is the largest contribution. Out of these 707, it is 640. And here are the various data points with various improvements as we approach the continuum limit. So you can see the red points or the blue points or some gray points, and that's obtained at this lattice spacing. When we move closer, that's what we obtain, even closer, even finer lattice, and then based on these 1, 2, 3, 4, 5, 6 lattice spacings, you can go all the way to the continuum. And that's what you obtain. And using these millions of extrapolations, we can also give an estimate on the systematic errors. And that brings me to my summary. So the various contributions in these calculations are listed here. We are hoping that other groups will calculate these contributions and either confirm or refute them. And then we will really see if the 707 is the correct answer. And we will see if there is any room for a new interaction, a new force, or perhaps not that many. The tension is far less than people thought for many, many years. And this ends my talk, and I thank you very much for your attention.
Thanks very much, Zoltan, for this very complete review of the status of the muon geometry.
So that was the plan, 50 minutes talk and 10 minutes.
You did it perfectly. Thanks a lot.
Okay.
So we have now time for questions and comments. So if anybody wants to ask a question, please go ahead directly. Yes, so Jose Francisco.
Oh, Jose can go ahead.
Okay, thank you, Usman. Thank you very much for the talk, Zoltan. So I wanted to ask you, what is your opinion on the possible differences between the white paper value and your value, like the theory or what? So thank you.
So as I said, the discrepancy between the white paper value and our value is about 2.1 sigma. And I wouldn't worry about that. If you found a 2.1 sigma discrepancy, you might be invited somewhere, but you have to pay for your trip, as I sarcastically commented on that. But if you go to the window observable, then here we have already a 3.7 sigma discrepancy, and that is far more worrisome. But the good news is that it is far easier to check these discrepancy. So I would wait until our colleagues will have a more precise determination of the window observable, and then we really see if there is any tension or discrepancy between the R ratio and the lattice result. But let me emphasize at this point that even the R ratio technique had a couple of not very nice features. The R ratio is dominated by two experiments, the so-called Babar and Chloe experiments. And in the most important region, from 600 to 900 MeV, there is a 3 sigma discrepancy between the two experiments. So if we are speaking about 3.7 sigma between experiment and lattice, but the experiment itself has a 3 sigma discrepancy, then it's also worrisome. The people who are calculating the AMU based on the R ratio method are taking into account this discrepancy. They are inflating their errors. There is a technique given in the particle data group. And when we calculated this number, we also inflated the error according to the particle data group. But obviously, if you had two results which are 3 sigma away from each other, then probably one of them is wrong. So just inflating the error does not mean that we singled out the good one out of the two dominant experimental result. But as I said, I would wait for the others, and then we can say a little bit more about this question. Did I answer your question?
Sorry, can I ask my question because it directly relates to what you're saying?
Sure, absolutely.
Do you have any idea about the time scale of the other results? I mean, in your community, you must talk about this often, or you must hear how they are doing, or maybe they say, yeah, we will be ready in a month. Or what is the time scale? When can we expect something?
So we originally put the paper out in 2020 February, and I had a bad experience some 15 years ago when the transition temperature of the QCD transition was calculated, and two very different results were on the market. One of them was our result, and the other result was the Brookhaven, Columbia, Reek, and Milk result. And that caused a lot of confusion and problem in the whole community, and even somehow reduced the reputation of Lattice QCD, because if people are 5 sigma away from each other, then it's not a serious science. And 15 years ago, I tried to convince my competitor that we should discuss and come out with a result when we are absolutely sure. And I tried to do that this time too. So I asked all the collaborations to have some strategy to compare our results before we come out. And actually, none of them was successful. They didn't want to do that step by no means. So they said everybody should publish their own results, and if it is a mess, then it is a mess. And a little bit, this is the situation. Almost 2 years has gone, and not even the window is calculated within these 2 years, which is somewhat surprising because, as I said, this is 1% of the manpower and 1%, 1 or 2% of the computational sources. From the RBC collaboration, who are the smallest one and almost the same as the R ratio method, they originally said that until the start of the semester, the fall semester, then it became Christmas, and now they say that within 4 to 6 weeks they will be out. So that's a very good news, I would say. Then the MINDS, here it is. They also say that between 6 to 8 weeks they will be out with the result. But all these results will be just window results. But at least that's also something. The problem with the RBC result that their new result will have 3 lattice spacings, 3. This one is only 2 lattice spacings. But unfortunately, the 3rd lattice spacing will be only 15% smaller than the previous lattice spacing. And we all know that 15% is not a very large lever arm. The MINDS result is far better on that respect, but they have non-physical quark masses. So there will be a problem or a difficulty extrapolating to the quark masses. But all in all, I would say that there will be some results on the window observables in a few months. Did I answer your question?
Yes, you did. Thanks a lot.
Very, very detailed way. Yeah.
Other questions from the audience? Yes, I see Gonzalo has his hand raised.
Hi, Zoltan. Thank you very much for your talk. I wanted to ask that in the plot you show of the 3 values, the white paper, the QCD, the Lattice QCD1 and the experiment, the Lattice QCD1 is the one with the biggest error bars. So I wanted to ask, like, what's the plan to make these error bars smaller, and how difficult is it?
Yes. So actually, it is about the same error bar as the most recent Fermilab result. So even if you average the Fermilab and the Brookhaven result, then you have a square root of 2 reduction in the error. But this is a very important question, and the answer is quite complex, if I can say. So this is our result. As you see, the statistical error is subdominant compared to the systematic error. So the total error is just 10% larger than the systematic error. So if you ask me if there is any way to reduce the error on the lattice, then we should probably reduce the error on the systematic size. And here in this table, you can look for the largest systematic errors. The connected light is 4.2. So it is almost the total systematic error. And I don't go through all of them, but the finite size effect is also 2.5. So this is the dominant systematic error, and this is the next to dominant systematic error. So the best way to reduce these error is to reduce the systematic error on the connected light and the systematic error on the finite size. And the systematic error on the connected light is coming from these spread of the continuum extrapolations. And the best way to avoid it or to reduce it, to have a lattice spacing somewhere here, because then the extrapolations are more constrained and the spread will be smaller. So this is the way to get a better uncertainty on this largest part. And if we go back to here, to the finite volume corrections, then here, even increasing the statistics would reduce the error. So the two most obvious ways to reduce the error is reducing the error on the finite size effect, which means increasing the statistics on existing lattice configurations. And the other one, perhaps even more important, is the introduction of a new lattice spacing to reduce the continuum extrapolation error. Did I answer your question?
Yes, yes, thank you very much. It was very clear.
Sure.
Other questions for Zoltan?
Zoltan, your lightest, your smallest lattice spacing is already quite fine, no? So do you have, are you affected by freezing? How would you expect that to affect, if you're mentioning now that you would go to even smaller lattice spacing? So
Yes, yes. So here is the list of the lattice spacings.
.05 was the lightest, or
64.
yeah, 0.06. Yeah.
Here it is. So 0.064 was the
So
lightest.
you are still
So we still have
some room.
Some room. The reason why we were not able to go even further down is that the enormous computational costs.
Sure.
So even for 64, a 6 Fermi box is huge.
Yes.
And the freezing would appear below 0.05. That means 0.05, that is 15, so 30% larger is still. So if we choose a lattice spacing, which is 0.05, that is still relatively stable for the freezing or absent the freezing problem, and it has a 30% larger lattice spacing what we have on tape. So a square, which would be the extrapolation, the easiest way of extrapolation. There are many, many more details on the extrapolation. That would be something like 70 or 80% larger a square, what we have today, what we could have in a few years. Did I answer your question?
Yes, thank you.
So it wouldn't be a factor of 2 lever arm, but almost.
Further questions? I actually have a comment on the question. So with respect to your comment about the other lattice results, so there is some degree of coordination among the groups in the context of this g-2 theory initiative. So there are frequent workshops in which people are discussing the results. So my impression is that your result has made the stakes very high and people are extremely careful now in publishing their final results. So maybe this is why things are a bit slowing down. It's just that people just want to be extremely do as much checks as they can in order to secure their results.
Yes, yes, that's probably true. Yeah.
So that is my feeling of why things are
Yes,
taking a bit
yes.
longer.
Yes.
Another comment is that with respect to the MINES results, so the one on the top on the right panel, there will be physical point simulations included in that result coming from the CLS ensembles. And the plan is also to include very fine lattice spacings around 0.04 Fermi. So that I think will nicely complement your studies in the sense that it goes really to
absolutely. I mean,
very fine lattice spacings, which are crucial, as you mentioned.
Yeah.
So this brings me to my question. You published your preprint in February 2020. So some time has passed since then. So what are your plans? What are you working on in this respect? What shall we expect from your group in the coming years or months?
Yeah. So my original idea, and I don't know, are we still recording or we are not recording anymore?
We can stop the recording, I think, at this point. If you wish.